Welcome to the lecture where we will be discussing AI deep generative models, PhDAI730, and this is your lecture number 8. Professor Tifreed Muhammad. In this lecture, we will be looking at deep generative models, on the other hand, are transforming the way we approach data generation and synthesis. These models, which include variational autoencoders and generative adversarial networks or GANs, are capable of generating realistic synthetic data that can be used to augment existing datasets or simulate new ones. This is particularly useful in scenarios where data is scarce and or difficult to obtain. By generating synthetic data, deep generative models enable more robust statistical analysis and provide new insights into the underlying data distribution. These models can be used to explore what-if scenarios, permitting researchers to test hypotheses and gain a deeper understanding of the data generating process. Through practical applications and hands-on exercises, we will delve into how these advanced techniques enhance statistical analysis and provide innovative solutions to complex data challenges. Now let's look into deep generative models into a little bit more depth, where models that use deep learning to generate new realistic data resembling the training dataset, creating synthetic images of human faces that don't exist in reality but look authentic. These models represent a groundbreaking advancement in artificial intelligence, enabling machines to create new realistic data that mirrors the complexity and diversity of real-world information. These models, such as variational autoencoders and generative deep adversarial networks or GANs, leverage deep learning techniques to understand the underlying patterns in existing datasets and generate synthetic data that is often indistinguishable from real data. By doing so, they address critical challenges like data security, privacy concerns, and need for robust testing environments. For instance, in healthcare, generative models can produce synthetic medical images to train diagnostic algorithms without compromising patients' confidentiality. While in the creative fields, they can generate original art, music, or even entire virtual worlds. The impact of deep generative models extend far beyond augmentation, offering transformative potential across industries. In research, they allow scientists to explore what-if scenarios by simulating hypothetical conditions, such as effects of climate change or new drug interactions, without real-world experimentation. Businesses use these models to enhance customer experience, like generating personalized fashion design or creating immersive gaming environments. As these models continue to evolve, their ability to generate increasingly realistic and diverse data will unlock new possibilities for innovation, making them indispensable tool for solving complex problems and driving progress in field ranging from healthcare to entertainment. Variation encoders, autoencoders. The VAEs generate data by learning a probabilistic distribution of the input and sampling from it, generating new handwritten digits similar to those in the MNIST dataset as an example. However, we'll look into more depth to understand these VAEs in a little bit more clarity. Variational and autoencoders, also known as VAEs, are a class of deep generative models that combine the principles of neural networks with probabilistic modeling to generate new data samples. Unlike traditional autoencoders, which focus on reconstructing input data. VAEs introduce a probabilistic twist by learning the underlying distribution of the data. This allows them to generate diverse and realistic outputs by sampling from a latent space, a compressed representation of the input data. VAEs consist of two main components: an encoder, which maps input data into the latent space, and a decoder, which reconstructs data from this space. By enforcing a structured continuous latent space, VAEs ensure that small changes in the latent variables result in meaningful variations in the generated data. This property makes them particularly useful for tasks like image generation, anomaly detection, and data interpolation, where understanding the data distribution is crucial. VAEs have found applications in a wide range of fields due to their ability to generate high quality synthetic data. For example, in healthcare, VAEs can create synthetic medical images to augment limited data sets, improving the training and of the diagnostic AI systems. In creative industries, they are used to generate novel designs such as fashion items or artwork by exploring the learned latent space. VAEs are valuable in unsupervised learning tasks such as clustering and dimensionality reduction, where they help uncover hidden patterns in complex datasets. Their versatility and ability to balance reconstruction accuracy with generative capabilities make VAEs a powerful tool for both research and practical applications. From enhancing data privacy to enabling innovative solutions in AI driven creativity is the core idea. GANs pit two neural networks against each other. A generator creates data and discriminator evaluates its authenticity, designing realistic fashion items for variety or virtual try-on applications is an example of GANs. So let's look into GANs with a very little example to understand it in more depth. Generative adversarial networks, or GANs, are a revolutionary class of deep generative models introduced by Ian Goodfellow in 2014, designed to create highly realistic synthetic data by pitting two neural networks against each other in a competitive framework, as mentioned earlier. The architecture consists of a generator, which produces data samples like images, text, or audio, and a discriminator, which evaluates whether these samples are real or fake. This adversarial process drives both networks to improve continuously. GANs excel at capturing intricate data distributions, enabling them to generate photorealistic images, deepfake videos, and even synthetic voices that are often indistinguishable from real ones. Their ability to model complex high-dimensional data has led to groundbreaking applications in the fields like art, entertainment, and medicine, such as creating lifelike avatars, enhancing low-resolution images, or generating synthetic medical data for research while preserving privacy. By pushing the boundaries of what AI can create, GANs have become a cornerstone of modern generative AI, inspiring innovations in creative industries, data augmentation, and beyond. Data augmentation: deep generative models create synthetic data that expand limited data sets, improving model training, as discussed earlier. Generating additional medical images to train AI for rare diseases is an example here. Synthetic data for privacy: generating artificial data that mimics real data without exposing sensitive information. Creating synthetic patient records, as discussed earlier, for research while protecting privacy is an important area also. Exploring what if scenarios, as discussed earlier, models simulate hypothetical situations to test outcomes and understand data dynamics. Simulating the impact of climate change on crop yields is a good example. Let's dig into this in a little bit more depth. So let us dig deep in simulating the impact of climate change on crops yield. It is a critical application of advanced computational models. This enables researchers and policymakers to anticipate and mitigate the challenges posed by a rapidly changing environment. By integrating data on temperature fluctuations, precipitation patterns, soil conditions, and atmospheric carbon dioxide levels, these simulations use machine learning and climate models to project how different crops will respond to future climate scenarios. For example, rising temperatures and erratic rainfall can stress crops like wheat, maize, and rice, leading to reduced yields or altered growing seasons. Such simulations help identify vulnerable regions and crops, permitting farmers and agricultural planners to adopt adaptive strategies such as switching to drought resistant varieties or adjusting planting schedules to safeguard food security in the face of climate uncertainty. The insights gained from these simulations extend beyond immediate agricultural practices, offering broader implications for global food systems and economic stability. For instance, models can predict how shifts in crop productivity might affect commodity prices, trade flows, and food availability, particularly in developing nations where subsistence farming is prevalent. Additionally, simulations can explore the effectiveness of mitigation strategies such as precision irrigation or carbon sequestration techniques. In contracting all these adverse climate effects by providing a data driven foundation for decision making. These tools empower stakeholders from local farmers to international organizations to develop resilient agricultural systems that can withstand the challenges of a warming planet, ensuring sustainable food production for future generations. Enhancing statistical analysis. Synthetic data enables robust statistical testing and validation of hypotheses, generating synthetic sales data to test marketing strategies. You can take an example for Walmart or Target or Lowe's or Home Depot, where the data is available in vast folders, vast Excel sheets, databases, and the PDF forms. However, when it comes to a customer information data that we would like not to expose that out when we are contracting an analytical firm to look into the statistical analysis to produce 2027, 2028, or 2029, even up to 2030 data, that how the sales would look like of any of these by applying the predictive analytics on top of their current data sets. That's where the synthetic data comes in handy for us to work with. Applications in art and design. Generative models create original artworks, music, or design based on learned patterns. AI generated paintings sold at auctions as unique artworks. Obviously, this is an area which is yet to go in quite depth in analysis. However, statistical probability and plausibility discussions permit us to look into a possible raise in the tone when it is music, or the notes which are being played by the artificially intelligent agent, how the statistics is helpful in expanding those tonalities associated with the tones that we are hearing in terms of the tunes, and auto tune the future music and closes this into a timely fashion, so we are just not bored with a non-stop hearing something that is synthetically created. Drug discovery is an important area, and models generate molecular structure for potential new drugs, accelerating research, designing novel compounds to target specific diseases like cancer, and that is an area in life sciences that uses statistics in quite detail. Video game development, generating realistic environments, characters, or textures for immersive gaming experiences. Procedurally generating landscapes in open world games. Let's look into this in a little bit more depth. The deep generative models are changing the way video games are designed and developed by making it easier to create rich, dynamic, and realistic content. These models like GANs or generative adversarial networks and VAEs, the variational autoencoders as discussed earlier, can automatically generate textures, characters, landscapes, and even entire game levels without requiring artists to manually design every detail. For example, a game developer can use a generative model to create unique forests, mountains, or critics in terms of the cities that look different every time a player starts a new game. This not only saves time and efforts, but also makes games more engaging by offering players fresh and unpredictable experiences. Additionally, generative models can help design non-player characters with diverse appearances and behaviors, making game world feel more alive and immersive. Another exciting application of deep generative models is in game development is in procedural storytelling and adaptive gameplay. These models can generate unique storylines, quests, or dialogues based on a popular player actions, creating a personalized experience for each user, for areas to explore or puzzles to solve. Generative models can also improve game testing by simulating countless scenarios and player behaviors, helping the developers identify bugs or balance issues before the game is released. By using these advanced tools, game developers can focus more on creativity and innovation, while AI enables the heavy lifting of content creation, leading to more diverse, engaging, and high quality games. Voice and speech synthesis. Creating natural sounding speech or voices for virtual assistants and entertainment. It involves music and playing songs or even singing songs. Suno.ai. Suno.ai is an example. AI generated voiceovers for audio books or animations is another example. Financial modeling, simulating market scenarios to test investment strategies and risk management, generating synthetic stock market data to backtest trading algorithms to provide a prediction on top of which a financial analyst will make a call to buy or sell or to hold the position. Autonomous vehicle training, creating diverse driving scenarios to train self-driving cars in virtual environments and other examples. Simulating rare weather conditions for safer autonomous navigation is an area that you can dig deep into. Fashion and retail, designing virtual clothing or accessories for digital try-ons and personalized shopping. AI generated fashion collections showcased in virtual showrooms. So if you have had a chance to look into the metaverse, You might have figured out that in metaverse there were clothes shops, there were shoe shops, and your avatar used to go and try on those things to buy in the virtual world. Healthcare imaging is another area that we have been discussing a while in the statistical applications in the artificial intelligence arena, generating synthetic medical images to improve diagnostic tools and AI training, creating synthetic x rays to train radiologists in detecting abnormalities is an area of its own. Future of deep generative models. Continued advancements will enable even more realistic and diverse data generation. AI creating entire virtual worlds for education, entertainment, and research, and we have been witnessing the change that is coming in since the arrival of the Chat GPT, Claude, Gemini, Mistral, or something like that. Happy learning. See you in the next lecture.